Hi, my name is Fyodor, and today I'm gonna show you some tricks and tips to solve equations in integer numbers. Those problems were given at various math Olympiads and competitions around the world, and also my home country. And this video will give you some easier examples of this kind of equations, but it's a good start. So let's see the first one. This problem asks you to solve the equation xy squared plus xy equaling 2 at the power xy. The most approachable idea is to give common factor xy times xy plus 1, which equals 2 at the power xy. We see that the right term has only 2 as a prime factor, but between these two numbers xy and xy plus 1, one of them is odd, so it has an divisor. Let's call it p prime with p odd. So if this number, call it a, has from one point of view only 2 as a prime factor, and on the other hand it has a prime factor p, which is odd. This is a contradiction, so our equation doesn't have hasn't any solutions in the integer or natural numbers. We could try something else. Also, another method to solve this problem is to remark that xy belongs to the set 10, 11, 12, 99. So xy squared is between 100 and 9801. So xy squared plus xy belongs to the set 110 dots 9900. But from this remark we deduce that 2 at the power xy belongs to the set 109,900. So xy cannot be greater than 14, because so xy is less or equal than 13, because 2 at the 14 power is 16,000 and something like that. I don't know exactly. I guess 60,192. So we have four possibilities. In the first case, we have xy equals to 0, which is not a solution, because 10 squared plus 10 is 110. Also, neither 11, 12 or 13 are solutions. You can verify yourself if you want. This is one easy problem, and I found it at the 5th grade Olympiad, and these kind of problems are given often in my country. Another type of problem is to find, for example, free numbers from the rational numbers and strictly positive with the given relations as here: x at the n power equals to y times z, z, and also the symmetrical relations where n is a natural or integer numbers, positive integer. Response. Well, if we multiply this the first relation by x, it results that x at the n plus 1 power is x times y times z. Also, it holds the next two relations, and we can deduce that x at the n plus 1 equals to y at the n plus 1 equals to z at the n plus 1 power. From that, we deduce immediately that x equals y equals z. Now, if n is 2, we have the relations as above. X squared is y times z, y squared is x times z, and z squared is x times y. And don't forget about the equality between x and y and z. So we have x squared equals x squared, etc. So all the pairs for the case that when n equals 2, for this case, all the pairs x, y, and z from the cube at the third power, which is the Cartesian product of sets, all them are solutions. X, x, and x, not x, y, z, x, 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 because we deduce that for n equal 2, that these relations are obvious. Now, if n is different from 2, we have that x and the n plus 1 power equals x squared, x at the n power, right? Which is true only for x equals 1. Why? Because x is strictly positive. It belongs to q plus n star set, right? Good. As a homework or generalizing this problem, I propose you to solve the next equation: x1 at the n power equals x2, x3, x index n, and yes, okay. Solve this equation, the system of equations in the set q plus star, right? Okay, the next type of equations is this one. If we write let's continue with equation number 3. Solve in natural integer numbers for at the x power plus 3 at the y power plus 6 at the z power equals 1540. Well, we firstly remark that the number in the middle is always odd. So if we pass in the right side 4 at the x power and 6 at the z power, we obtain an odd power equals an even an odd number equaling an even number. So this is impossible. So we deduce that one of the numbers is obviously odd. So 4 at the x power is 1, or 6 at the z power is 1. We suppose that x equals 1, first case. In this case, we deduce that 3 at the y power is 1539 minus 6 at the z power. Well, z cannot be very large. It can have a range of values from the set 1, 2, 3, and 4, because 6 at the 5th power is 1296 times 6, which is anyway larger than 7,000, and obviously we have to try every value possible. If we try, for example, z equaling 4, then 3 at the y power is this minus 1296, which is 243, and luckily we have a solution for this. It is y equals to 5. Now if we try for z equaling 3, it results that 3 at the y power is 1539 minus 216, which is 1383, which doesn't have any solutions in the integer set of numbers. Also, if we try z equaling 2 and z equaling 1, we don't have any solutions. Doesn't provide any solutions. So it doesn't match our request. But if z equals 0, so if in the second case, if z equals 0, we deduce that 3 at the y power equals 1539 minus 4 at the x power. Here are much more solutions or possibilities than we could imagine. Actually, there are only 5. From this one, from this it results that x belongs to the set 1, 2, 3, 4 and 5. If x equals to 5, 3 at the y power is 515, is not an option. X equals to 4, then we have 1200 and I don't know 83, I guess, which obviously is not an option. X equals to 3, x equals to 2, x equals to 1 are not solutions. So the only solution of our problem is the pair, the order pair 0, 5 and 4. This is the only solution. Well, this is only our only option. There are many types of other equations of this kind. Pretty much the same solving method, but as a homework I recommended to try the next problem. For example, try to solve in integer numbers set the equation x squared plus 2005 equaling 3 times y squared. Problem number 2. X and the 2y power equals 240 plus x and the y power 3. Find the integer numbers x and y if this relation holds true for x and y numbers. I wish you best of luck, and you can find at my address below discussions about this type of equations, and also on my website mathsdiscovery.com. Thank you very much for watching my video, and I hope you join my channel and watching further videos on the future. Good luck.